Hello everyone. So in this session we'll be discussing the life science gate questions that are related to UV visible spectroscopy. So the question which we have taken today is the question number 16 from biochemistry section from the life sciences question paper that has appeared in 2020. So this question states that a solution absorbs 20% of the incident light in a cuvette of path length 1 centimeter. The amount of light transmitted by the same solution in a cuvette of 3 centimeter path length is rounded off to 1 decimal place. Okay. So before starting this, let's understand some of the basics of spectroscopy. So, what is spectroscopy? Why do we use spectroscopy? Okay, so it is a technique that is used to study the interaction between the electromagnetic radiation and the matter. Okay, so spectroscopy is a study of the interaction between electromagnetic radiation, so we can call it EMR, and the matter. Okay, this matter could be any atom, like any molecule, any ion, anything. This matter could be anything, and electromagnetic radiation. So electromagnetic radiation, we know it is a whole spectra of light. Okay, so whole spectra of light. So light has certain amount of energy. So this energy is inversely proportional to its wavelength. Okay, so energy is inversely proportional to its wavelength. That means shorter wavelength of light carry more energy and longer wavelength of light carry less energy. Okay, so uh, in the wavelength, increasing wavelength, if we'll see, so we have gamma rays, x-rays, we have gamma rays, we have x-rays, and then we have UV range, we have UV rays, we have visible range, and after the visible range we have further IR waves and radio waves, microwaves. Okay, so these are in increasing order of wavelength, and we just said the more the wavelength, lesser the energy. Okay, so the shorter wavelength lights are having more energy. Okay, more energy, less wavelength. Okay, so gamma rays, x-rays have very high energy and lesser wavelength. Okay, and UV rays, visible rays, having higher wavelength, comparatively lesser energy. Okay, and okay, and also the frequency. So this is the whole spectra. So the molecule, okay, this EMR, or the electromagnetic radiation, when it passes through a molecule, okay, A, it can absorb this light. Okay, B, it can emit this light. Okay, or uh, okay, and C, it can scatter that light. Okay, so based on the type of the type of uh, reaction the molecule is given, according to that we have several different spectroscopy. Okay, so if the molecule is absorbing, we'll have the absorption spectroscopy, emission spectroscopy, scattering spectroscopy. So here we are talking about the absorption spectroscopy. Okay, and these, a specific amount of energy is needed to promote electron in a substance to a higher energy state which can detect as absorption. Okay, so uh, you have a very simple setup of this spectroscopy I'm drawing here. So UV visible spectroscopy contains this range of UV rays and visible range. Okay, so visible range starts from nearly 400, 380, or we can just say nearly 400 nanometer range to 800 nanometer range. Okay, and UV range we generally follow 200 nanometer to 400 nanometer range. So this particular entire range is used and called as UV visible range. Okay, and this range we use for UV visible spectroscopy. We excite the molecule or the electron within it using the UV visible uh, rays. Okay, so as I have already said that electrons or the molecules get excited by a particular wavelength of the light. Okay, so if we have one light source, okay, we have one light source. So as it is the source light, it contains all different kind of lights or wavelength of lights. Okay, so all wavelength of lights is containing in this particular light source. But as we know that the molecule will get excited at a particular wavelength, so we set a monochromator. Okay, a monochromator in it. So a monochromator is having a prism, okay, which will take up the light and differentiate or it to its components, okay, to different wavelength of light. Okay, so it is a monochromator. So it selects any particular wavelength that we can adjust according to the angle and the filter. Okay, so only one particular wavelength light will go further when passes through this monochromator. Okay, so this monochromator allow to pass only one particular wavelength of the light, and that wavelength of the light now that passes with the sample. Okay, the sample which we have in a cuvette, we have some sample. Okay, so this light is passing through this sample. Okay, so if electron is getting excited using this energy, okay, so electron excitement means generally electrons remain in the ground state, but upon the excitement it goes to the higher energy state. Okay, the excited state. So to go from ground state to higher energy state, it requires some energy. So that energy it gets through the light, from the light source. Okay, and so that we can say that this electron absorbs some of the light and go to the higher energy state. Now after when this light crosses this particular sample and further moves ahead, as some of the part of this light or energy of this light has been already absorbed by the electron, not the total amount of light will going to leave from here. Suppose if you have given 100% intensity light, as the sum of the light is being absorbed in the sample, on a lesser intensity of light will further pass from the sample. Okay, so suppose 90% of the light is absorbed here, so only 10% of light will further move or transmitted through the sample. Okay, and this particular light gets detected by detector. We have one detector, and this detector identifies this light and converts into electronic signal that will read by the system, or we can say computer, and give us the value of any form like absorbance, concentration. Okay, so that value we get from the computer, but how these calculations are being done, that we have to understand. Okay, so suppose you are giving the intensity of the light which is going to the sample is 100%, that we are referring as I naught, but as some of the light is being absorbed here, so the transmitted light which we are referring as I is less. Okay, so if there is a absorbing substance in the solution, or in the sample, in your sample, if it has some absorbing substance, then absorbance should would be greater than 0, and the transmittance will not be 100%, it would be less than 100%. Okay, if any absorbing molecule is there. Okay, so transmittance we can define as the amount of light emitted after absorption. So that is our transmittance, the amount of light emitting after the absorption. So for transmittance we can write transmittance will be I upon I naught. Okay, from the total how much light is the is transmitted. Okay, so as we are seeing here, 10% light is transmitted out of 100%, so transmittance is 1/10. Okay, so whatever light is given, 1/10 of the light is only being transmitted, another portion of the light is being absorbed. Okay, but our calculations or all the values or the concentration of the sample it is not directly related with the transmittance, but instead of transmittance it is related to the absorbance. Okay, so okay, so it is related to the absorbance. So now we have to set up a relation between transmittance and absorbance, because suppose if I brought a graph this between concentration of the sample and the transmittance, if uh, uh, the transmittance is 100%. Okay, so if no, if it not concentration, if the transmittance is 100%, I'll put a value here. Okay, transmittance 100%, nothing is absorbed, then transmittance will be 100%. Okay, if some light is absorbed, the transmittance will further decrease, and then if more light is absorbed, transmittance will further decrease, so it will keep on decreasing, it will keep on decreasing. So more the concentration of the sample, more the transmittance, or lesser the transmittance would be. Okay, the more the concentration, lesser would be the transmittance. But in this condition we'll get a graph something like this, something like this. Okay, so now at this condition, finding out the concentration or finding out the value of higher concentration sample would be very difficult, because if we correlate with transmittance, it will be very less. If the concentration would be high, the transmittance will be very less, it will be very bottom of the graph. Okay, so that is how if we'll calculate the concentration of the sample based on transmittance, it would be very difficult. But if we can convert the same thing in a linear graph, and that is also which is going upwards or which is going further, that would be better, and that we can only get when we put our values in form of absorbance. Okay, this is not transmittance, this is concentration. Okay, so in form of absorbance, so more the concentration, higher the absorbance. Okay, less absorbance, less concentration, more absorbance, more concentration. Then furthermore, in the linear graph we can easily calculate the concentration of the sample rather than calculating it using transmittance. So we have to calculate our value of transmittance in form of absorbance. Okay, so if we have to set up a relation between transmittance and absorbance, okay, so as we have already seen, our transmittance is T is equal to I upon I naught. I is transmitted light and I naught is the total light. Okay, so if we have to calculate the absorbance, that will be the minus log of T, transmittance. Okay, so or we can also write log of reciprocal of transmittance. Okay, also we can write the same thing. If we'll put the value of T, then it will become I naught upon I. So this is the formula to calculate the absorbance of I naught upon I. Okay, and using and getting, and when we get this absorbance, we can calculate the concentration of the sample using the Beer-Lambert's law, that is A is equal to ECL. This is Beer-Lambert's law. Okay, so here E is the molar extension coefficient, C is the concentration, and L is the path length. Okay, A is our absorbance, E is the molar extension coefficient, L is the path length, L is the path length of that path length or the length of the cuvette. Okay, so absorbance would be ECL. That is the Beer-Lambert law. So once we get the value of absorbance, we have the value of molar extension coefficient, we know the length of the cuvette that we are using, we can easily calculate the C, that is the concentration of that sample. Okay, so the more the concentration, the more will be the absorbance. Okay, so if now we'll see our question. The question is, a solution absorbs 20% of the incident light. So if we consider our incident light is 100%, then it is saying that absorbance is 20%. If absorbance is 20%, the transmittance would be the remaining light. Okay, that means 80% is the transmitted light. Okay, or we can say I. And the cuvette of path length of 1 centimeter. The amount of light transmitted by the same solution, a cuvette of 3 centimeter. So it has been asked to us, when the path length L value is 3, what would be the amount of transmitted light? We know that amount of transmitted light is 80% in 1 centimeter cubed. So to put it in Beer-Lambert's formula, first so this is ECL. A we know, we can write as log I naught on I. E and C values are not given. We have the values of path length, which is 1 centimeter. Okay, we have this I naught value, log 100 divided by 80 is equal to EC, or we can say log 100 minus log 80 is equal to EC. Log 10 value, log 10 value is, I know, let's see the log 10 value, log 100 value. Log 100 value is 2. Log 100 value is 2, and log 80 value is 1.9 is EC. So EC is equal to zero point 0.1. Okay, EC is equal to 0.1. So now we have to find out the same transmittance in, so if I'll write it here. Okay, so we have to find out the new transmittance EC, and L is given to us 3 centimeter. Okay, so 100, we know the value of EC is 0.1 into 3, so that will be 0.3. So to find out IT, we have to take antilog, this antilog of 0.3. So antilog of 0.3 is, antilog of 0.3 will be 0.3 is 1.995. So IT would be, or we can also say 2. That means 50%. That means 50% will be the transmittance. Or if we'll solve this, it will come some 50.12% something. Okay, because the question is asked in question rounded off to 1 decimal point. So it will be 50.1%. Okay, I hope it is clear. And this is my NPTEL reference. Thank you.